So let's go ahead and look at balancing chemical reactions. A chemical reaction is what's actually reacting and producing something. It represents what's actually happening in whatever your mixture is. A chemical equation is how we represent what's happening. So we say balancing chemical reactions. Truthfully, it's probably better terminology to say balancing chemical equations because they are equations. Your reactants, what's in your reactants, is equal to what's in your products. Law of conservation of mass. I cannot create nor destroy matter. So, in order to correctly calculate the quantities in chemical reactions, we have to balance this equation. We must use balanced equations to properly represent what we want or what we have. A chemical equation, again, is a symbolic representation of a chemical reaction. We use this to be able to tell us and others what's happening. We use this in the forms of symbols, meaning elemental symbols, most often elemental symbols, that is. We can also have symbols for heat, light. We can use catalysts. And there's other things that can be included as well. So we use different types of symbols to represent what's happening, what's reacting, what's being produced, and the formulas of different compounds. The reactants are always given on the left of the reaction or left of the equation, products to the right, and an arrow in the middle. Reactants are defined as the substances that are initially present in a chemical reaction. Your reactants are consumed during the reaction to make the products. And again, reactants reside on the left side of that arrow. So here we see our reactant side. Products are the substances that we form or produce in a chemical reaction, and we find those to the right of the arrow. So the arrow is what's going to separate out our reactants from our products. We do have a series of rules that we follow in order to balance equations. So you do need to be comfortable with these rules, and truthfully, the faster you just commit these rules to memory, the easier it'll be for you. I'm not saying that you have to be able to repeat them to me, but you need to be able to naturally use these rules while you're balancing your own equations. First thing you should do, identify the most complex substance you have. This could be a polyatomic, it could be something else, just find whatever's the most complex. And we're going to work a bunch of examples so you can kind of see how that works as well. Beginning with that substance, choose an element that appears in only one reactant and one product if possible. What I mean by that is sometimes you're going to have something such as the reaction balanced here. We see oxygen is only in one reactant, but it's in two products. We don't want to start with that. We want to start with something that's only in one reactant and one product, like the carbon or the hydrogen. You're going to adjust the coefficients to obtain the same number of atoms of this element on both sides of the equations. Balance polyatomic ions if present as a unit when possible. Not always, but oftentimes your polyatomics will stay together as a single unit. So oftentimes if I have sulfate over here, I'm going to have sulfate over here as well. Now, sulfate's going to be combined with something. Maybe I have sodium sulfate over here. And maybe I have calcium sulfate over here. I don't know. But it's still sulfate on both sides. We will do examples of the polyatomics staying together and the polyatomics breaking apart. If the polyatomic is broken apart into smaller units, obviously we cannot balance it as one unit. You then balance the remaining atoms. Use fractions if necessary, and I'll show you what I mean by fractions, and this is often needed if you have a diatomic. Remember, we have 7 diatomics. You've got H2. You've got, so that's on the one side of the table. Then go to your grouping of 7, N2, O2, F2, Cl2, Br2, and I2. If a fractional coefficient has been used, you must multiply both sides of the equation by the denominator to obtain whole numbers for all coefficients. We cannot leave a balanced chemical equation with fractions in it. There is very specific conditions under which we can leave fractions, and regular balancing is not the case. We will deal with some examples where we have to use fractions, but this is not it. So for today, all of your coefficients out front must be whole numbers. Check your work by counting the numbers of atoms of each kind on both sides of the equation to be sure the chemical equation is in fact balanced. What do I mean by counting atoms? Counting atoms in a chemical equation. When I look at this, here I've got aluminum sulfate written out. Okay, so we should know by now that we can call it aluminum sulfate. We should be able to split it apart. We've learned naming. We can call it aluminum sulfate. But what I have here, you need to recognize coefficients and subscripts. So the coefficient out front here, coefficients apply to the entire compound. So this means I have 2 aluminum sulfates, whether that be 2 compounds of aluminum sulfate, 2 moles of aluminum sulfate. I have 2 of this entire thing. Your subscripts apply to what precedes it. So here, where I've got the 2 following the aluminum, that means I have 2 aluminum ions. Here, where I've got the 3 following the parenthesis for the sulfate, that means I have 3 sulfates. So if I was to draw out what I have here, I have Al3+, Al3+, SO4 2-, SO4 2-, SO4 2-, and that's just for one of them. I have 2 overall, so I also have Al3+, Al3+, SO4 2-, SO4 2-, SO4 2-. All of this combined together represents what is written up here. So you need to be conscious and comfortable with what we mean by coefficients and subscripts. Coefficients go out front and apply to the entire molecule or compound. Subscripts only apply to what precedes them. So remember, a coefficient, the number out in front, is applied to all elements in the formula. So when I say 3KMnO4, that means I have 3 potassiums, because I'm going to distribute this through 3 manganese, and 12 oxygen, because there's a 4 down here for the oxygen, so 3 times 4 gives me 12 oxygens. A subscript is applied to the element it follows, not the whole molecule. So in this case, if I just had KMnO4 written out, I have 1 potassium, 1 manganese, and 4 oxygens. If a subscript follows the parentheses, it counts for the entire polyatomic. So here, aluminum sulfate, I have 2 aluminums, 3 sulfurs, and 12 oxygens. And that is because this 3 distributes through to the entire polyatomic, giving me my 3 sulfurs and 4 times 3 for oxygen, 12 oxygens. Another thing we do is you need to be comfortable with this, is using symbols in these equations. These symbols, we have symbols that represent the states, the physical state of the compound. We also have symbols that can be used to identify if we're using heat or light or a catalyst in the reaction itself. So first, let's talk about table 1.4 over here. This is straight from your textbook. You do need to be comfortable with this table, okay? So if you see, and if you have to write these out, you do the same thing. If you have something in the gas phase, you put a parenthesis, lowercase g, close parenthesis. So, for example, if I had chlorine gas, I would write Cl2, chlorine's a diatomic, parenthesis, lowercase g, close parenthesis. Liquid is a lowercase l. An example there, bromine, diatomic, is a liquid under room temperature conditions. A solid, lowercase s, I2, iodine, another one of your diatomics, is a solid under STP. We'll talk about what STP means, standard temperature and pressure, but also under room temperature conditions, iodine is a solid. The last one is AQ. AQ means dissolved in water. So if I wrote NaCl, AQ, that means that sodium chloride is dissolved in water. That's like taking a glass of water and dumping table salt into it. The sodium chloride exists as an aqueous phase. What's actually happening there then is I have sodium ions and chloride ions that are going to float around and be able to participate in chemistry. Why do I care about aqueous? Well, oftentimes these things are not able to react when they're in their solid form, but if we put them in water, they dissociate into the individual ions, and now they can do all kinds of things, and they can participate in all kinds of cool reactions. So aqueous is when aqueous causes ions or charged particles. I apologize, I'm trying to write this so you guys can read it. There's charged particles by themselves in solution. This will be explained in Chapter 5. We'll go into a lot more detail in Chapter 5, but you are responsible for recognizing that AQ means aqueous, which is going to create ions, which are charged particles floating around in solution. We also can use these symbols to represent if a reaction has been heated or light has been applied. This is often written above the arrow, such as we could have, say we have some random compound, XY, it's not actually an element, and we heat it, and we form X plus Y. Putting that little triangle here over the arrow means we've applied heat to the reaction. If I had XY, and I put this little H nu, giving me X plus Y, this is when we've used light in the reaction. Remember, H nu means photon. It's a photon of light. Catalysts can also be listed above the arrow. Here we see a catalyst listed above the arrow. MnO2 is acting as a catalyst in this case to break down peroxide. So if we have heat, light, catalysts, they'll often be listed like this above the arrow because they're not actually reactants. You're going to learn more about catalysts in second semester, but catalysts are not actually a reactant. They help speed up the reaction by finding a different pathway for the reaction to occur, but they are they're regenerated by the end of a reaction to keep the reaction keep going. So they're not actually consumed in a reaction, so they do not fall under the definition of a reactant. So instead, we write it over the arrow like that. So let's look at some balancing equations. We need an equal number of elements on each side of the equation, and be cautious of states of molecules here. Not all reactions you balance will have the states listed, but when you can put the states, or if they are there, if they are already there, you need to make sure to pay attention to them. If you can figure them out, if it's implied by the question or by the rules you know, you are responsible for them. In theory, though, this first reaction is balanced. Let's go ahead and count to make sure it's actually, in fact, balanced. The way I do this, and the way I find it to be easiest for my students, is I write down all the elements I have. I have iron, carbon, and oxygen. Iron, carbon, and oxygen. I then go through and write down how many of each do I have on each side of the reaction. Over here, I see iron is here only, but I do have a coefficient 4 out front. Remember that 4 is distributed through to the entire compound. So that means I have 4 irons present in this compound. I don't see any iron anywhere else, so I'm going to say I have 4 irons. Next, I have carbon. Only spot I have carbon is here, so therefore I also have 4 carbons. Next, I have oxygens. I see I've got 3 oxygens here, but that does need to be multiplied by the 4. And I also have 2 oxygens over here, so in total, I have 14 oxygen. That's what I currently have on my reactant side. Let's go ahead and look at our product side. I've got iron here, and there's 2 of them, but I have a coefficient 2 out front, so I have 4 irons. I have 1 carbon here, but I have a coefficient of 4 out front, so I have 4 carbons. Here I have 3 oxygen, but there's a coefficient out front, so that means 6 oxygens. Here I have 2 oxygens with a coefficient of 4 out front, which means 8 oxygens, overall 14 oxygens. So this reaction is in fact correctly balanced. When I count the elements on both sides of the reaction, this comes out as balanced. Now let's look at an example where it's not yet balanced. We need to do the same thing, but we need to figure out how do we adjust it to make sure it's balanced. We've got iron, oxygen, hydrogen, iron, oxygen, and hydrogen. The other thing I will warn you about is, you see here, I went through, I saw iron first and wrote that first, carbon next, wrote that next, then oxygen and wrote oxygen, oxygen matched. If I went on this side, I would write iron first, then oxygen, then carbon. I don't do that. I make sure that the elements match across here because otherwise I miss it. Well, maybe you're better than me at this. Maybe your eye cannot get distracted by that, but my eye gets very distracted. So it doesn't matter which order you write these down in. I write them in the order that matches when I first see them in the reactant side, and then I leave them there for the product side as well. So back to what we were doing. Let's see. We've got iron, and we've got 3 of them. Oxygen, we've got 4 of them. And hydrogen, we've got 2 of them. On the other side, iron, I've got 1 of them. Hydrogen, I've got 2 of them. Oxygen, I have 1 of them. How can I go about balancing this so that it actually balances and we have the same number of elements on each side? Well, the first thing I'm going to look at is I see, okay, iron, I have 3 here, I have 1 here. Iron's actually by itself over here. So I'm going to go ahead and put a coefficient of a 3 in front of that iron. That's going to multiply this by 3, and now I have 3 irons on each side of my reaction. Next, I look at oxygen. I have 4 on my reactant side and only 1 on my product side. So I'm going to multiply this by 4 by putting a coefficient of 4 in front of my water. Now my oxygens are balanced. But that messed up my hydrogens. Now I have 8 hydrogens over here. So now I need to look at my other side and say, okay, how can I fix my hydrogens? I have 2. I need to multiply that by 4 to get 8 hydrogens on that side as well. That should be a 4 there. So I'm going to rewrite this reaction so it's not quite as messy. Fe3O4 solid plus 4 H2 gas gives me 3 Fe solid plus 4 H2O liquid. And now my reaction is in fact correctly balanced. So again, I recommend doing the counting atoms method. I find it to be better for students. They tend to mess it up less and it makes more sense to most. Some students just want to kind of brute force go through the reaction and say, okay, well, I've got 3 irons, so I'm going to put 3 here, and then 4 oxygens here, 4 there. And that can work. But when the reaction or the equations get a little more complex, it can get really messy and students kind of get bogged down and confused. If you do this counting atoms method like this, you're less likely to get confused. Okay, let's look at a few more examples. We've got CO2O3 reacting with carbon. So this is cobalt, by the way. Reacting with carbon, producing CO, that is a lowercase o, so that is cobalt, plus CO2. First thing you should do is add up how many elements of each species do we have on each side of the equation. So I'm going to write down, I've got a cobalt, an oxygen, and a carbon. I'm going to follow the same format over here, and then I'm going to go through and figure out how many of each element I have. 2 cobalts, 3 oxygen, 1 carbon, 1 cobalt, 1 carbon, 2 oxygen. So first thing I'm going to see is that, okay, I'm going to tell you right now, when you have something like this where you've got an odd and an even going on, you need to multiply them by each other, like multiply the 3 by 2, multiply the 2 by 3 to make those things equal, because otherwise you're going to be fighting with that all day and it's not worth it. So I'm going to multiply this by 2 to give me 6 oxygen, multiply this by 3 to give me 6 oxygen. So when I do that, I need to put a 2 in front of my CO2O3 and a 3 in front of my CO2. But notice that that changed my cobalt on my reactant side, giving me now 4 cobalts, and it changed my carbon on my product side, now giving me 3 carbons. So I did change it because of oxygen, but I got to make sure to change everything. that should be written there. That looks better. So now I've got 4 cobalts on my reactant side. I need 4 cobalts on my product side. I've got 6 oxygens on each side. I've got 1 carbon on my reactant side, but 3 carbons on my product side, so I need to go ahead and multiply this by 3 as well to balance out my carbons. If you were to rewrite that equation, 2 moles of CO, 2O3, trying to emphasize that's the lowercase o is hard for me, plus 3 moles of carbon gives me 4 moles of CO plus 3 moles of CO2. And that is balanced. Okay, SrCl2 plus Li3PO4 give me Sr3PO42 and LiCl. You can, oftentimes I'll read them by formula, it's just faster for me, but you should be able to recognize the names of these as well. So you should recognize this as strontium chloride reacting with lithium phosphate to produce strontium phosphate and lithium chloride. If I gave you the names, you should be able to put them into formula for me as well. So I've got strontium, chloride, lithium, and phosphate. Strontium, chloride, lithium, and phosphate. And notice here I'm leaving the phosphate together because I've got phosphate here and phosphate here together. There's no reason to break that apart. It just complicates things to break it apart. On my reactant side, I start off with 1 strontium, 2 chlorides, 3 lithium, and 1 phosphate. On my product side, I start off with 3 strontiums, 1 chloride, 1 lithium, and 2 phosphates. So first, let's look at strontium. I've got 1 strontium on my reactant side and 3 on my product side. So I'm going to go ahead and multiply this by 3 to give me 3 strontium on each side. When I do that, that also multiplies my chlorides by 3. So now I have 6 chlorides on my reactant side. Let's balance out my chlorides. I have 6 on my reactant side. So I'm going to multiply this by 6 on my product side, giving me 6 chlorides on each side. When I do that though, now that also multiplies my lithium by 6. So now I have 6 lithiums on my product side. I have 3 on my reactant side. I'm going to go ahead and multiply that lithium by 2 to equal that out to 6 as well. So 2 in front of there. That fixes my lithium, but now I need to multiply that phosphate by 2. And if I look, actually that balances out my phosphate just perfectly because I have 2 phosphates on the other side as well. Go ahead and pause the video if you'd like to write this down. I'm going to erase it so I can rewrite the equation and you guys can actually see it without it completely mumbled up into everything else. So the balanced equation here, 3 moles strontium chloride plus 2 moles lithium phosphate, giving me 1 mole strontium phosphate and 6 moles of lithium chloride. Now let's look at an example where our polyatomic does not stay together. The example written on the top here, let me erase this for some space. This example here, we've got ammonium dichromate decomposing to form this chromium oxide, nitrogen, and water. This is technically chromium 3 oxide, if we want to be specific. And that's, we see that's the reaction that's actually shown in the picture here. It's ammonium dichromate is this like really pretty orange color. We heat it and it decomposes and it can form this brown, black, charcoal, not sure what color you want to call that. But it releases nitrogen gas, it releases water vapor, and then forms this solid chromium 3 oxide. In this case, though, I cannot leave the polyatomic together. So I've got to separate it out. I've got nitrogens, hydrogens, chromiums, and oxygens. So nitrogen, hydrogen, chromium, and oxygen. To start off, I see that I have 2 nitrogens, 8 hydrogens, 2 chromium, and 7 oxygen. Again, that's because I've got a 2 out here, so this 2 distributes through, giving me 2 nitrogen, and 2 times 4, 8 hydrogen. On the other side, I've got 2 nitrogens, 8 hydrogens, 2 chromium, and 7 oxygen. Yes, I've already got the 4 here. I didn't realize I left that balance to you guys. I wasn't meaning to leave that balance, but I did. So that actually works to our advantage. So this is actually balanced for us unintentionally. I thought I had erased that. Well, it worked out. We see here, though, the biggest point of this one is that we do need the 4 in front of here to balance out the reaction, but we see the polyatomic breaks down. So in the example here, with the strontium chloride reacting with lithium phosphate, the phosphate stayed together. We could balance that phosphate as one single unit. You are welcome to write it out. If you wrote this out looking at phosphorus and oxygen, you would see it does still in fact balance. It has to. Laws of conservation of mass states it must balance. But it just makes it faster and easier for us to leave the polyatomic together. But in this example, we see that the ammonium polyatomic is in fact breaking down to form nitrogen, and then some of the oxygen from the dichromate is forming this water vapor. So in this case, we could not leave the polyatomic together. But I thought this was kind of a cool example just because we do see a nice picture from your textbook actually showing what's breaking down here and what the colors look like. So a lot of times we do these reactions, we actually see the different colors being formed when something changes. I know I've said this before, but if you take Gen Chem lab in spring, you will do a dehydration of Epsom salt during your first lab period. And it's not per se exciting, but it's kind of cool that you take a compound that looks crystalline, it looks like a see-through crystal pretty much, and then you dry it and it looks like this hard white powder. And it's because you drove all the waters away. This isn't the exact same reaction, but it's the same kind of concept. We broke down the original compound and we formed this charcoal-looking gook, for lack of a better term. Okay, so when you're looking at reactions, what I need you to think about, especially if you're given words. So for example, here we wrote out aluminum metal reacts with air to produce a white powdery compound, aluminum oxide. The first thing I want you to do is ask yourself, what is reacting? Here, we've got aluminum metal reacting, aluminum metal, Al, solid, and it says it's reacting with air. Air does have a lot of things in it. It's 68% nitrogen, it's got the oxygen we breathe, it's got carbon dioxide. Depending on where you're at, it's got other things in it too. When we say reacting with air, though, we really mean it's reacting with O2. We're not saying it's reacting with O2, but that's what I mean in this example. We mean it's reacting with O2 because I know that aluminum can form aluminum oxide. How do I know it's reacting with oxygen? Because it's forming aluminum oxide. The oxygen has to come from somewhere. The oxygen comes from the air. So this question isn't explicitly written, but it's taking from the context of the question to figure out what's going on. And so you do have to sometimes delve into the context. It's kind of like when you're reading something, do you read the word read or read? You know, R-E-A-D, they're spelled the same way. Record and record, same thing. You're doing that in the context of chemistry as well. Sometimes you just have to pick up what you're doing based on the context of the question. And since it's telling me I'm forming an oxide here and I'm reacting with air, that means I'm really reacting with oxygen. So what's reacting? Aluminum metal and oxygen. Oxygen is a diatomic, so what's reacting is O2. What is being produced? Well, it says a white powdery compound, but in parentheses it says aluminum oxide. What are the formulas of each reactant and product? We've got aluminum metal. All metals except mercury will be solid under regular room temperature conditions. So unless specified, all metals will be considered solid. Oxygen is a gas under standard conditions. So unless specified, we assume oxygen is a gas. But you need to remember your diatomic and polyatomic atoms. polyatomic elements. So like S8, P4, that kind of thing. And your 7 diatomics. So when you say oxygen, we really mean O2. And your product, aluminum oxide, aluminum can only be a +3 charge. Oxygen is always a 2- charge. So when I cross those charges, in order to get an electrically neutral compound, it must have the formula Al2O3. And this is a solid because it says it's producing a white, powdery compound. White and powdery is not going to be a liquid, nor is it going to be a gas. White and powdery, white could be a liquid, yes, but powdery, that word powdery tells me it's a solid. So write the correct formulas for each species, check. Write the correct phases for each species, check. And then balance your overall reaction. Do not forget to balance the reaction, or the equation, because in one of the few coming modules in this chapter, we're going to have to use balanced equations to be able to determine what's reacting, what's being produced, and how much of something's reacting and being produced. And we need these proper multiple ratios to be able to answer these questions. So make sure at the very end, do not forget to balance. Sometimes I'll give you a balanced equation, but sometimes I won't. And so you need to quickly look at a reaction itself and say, okay, is this equation balanced? Okay, good, it is, and move forward. Or, oh, nope, it's not. I better balance that quick before I use it. And you have to be able to quickly recognize if it's been balanced or not.